Hi, it's Kate, and this is the third video for week 12 of Math 23. Now we're going to combine a couple of the topics that we've been discussing, derivatives, manifolds, and we're going to enter a discussion about critical points. That's right, maxima, minima, saddle points, all those things that you already know about. But now we need to talk about how and why they exist, how we find them in multiple dimensions, how we find them with more complicated functions of multiple variables, etc. So suppose we have a function that maps from Rn to R and it's differentiable at a point x0 and that the derivative of the function at x0 is not 0. Then that means there exists a vector v for which the directional derivative is not 0 at that point, and the function g of t equals, this is a little confusing, it should be written like this instead of how it is written. So g of t is equal to f of x0 plus tv, and that has a non-zero derivative at t equals 0. Because if t equals 0, then this would just be f of x0, and we know that f of x0 has a non-zero derivative. So even if we just consider the points that lie on a line through x0 with the direction vector v, the function cannot have a maximum or a minimum at x0, right? Its derivative is not 0 there. The function is either actively increasing as we travel through that point or actively decreasing as we travel through that point. So basically, in searching for a maximum or a minimum of this function at points where it is differentiable, we really are looking for points where the derivative of f is equal to 0. Those are what we call critical points. A critical point is not necessarily a maximum or a minimum, but there's a useful test that generalizes the second derivative test of single variable calculus. The proof is a little bit complicated. You can certainly read over it in Hubbard, but we're going to skip it. Basically, what we're going to do is we're going to form the Hessian matrix of second partial derivatives. So this is the recipe for calculating the Hessian matrix. And what this is saying here is that the ith row and the jth column of the Hessian matrix is a mixed partial. It's going to be first you take the derivative with respect to the ith variable, and then of f, and then you take the derivative with respect to the jth variable of f. So that is what we call a mixed partial. We're going to talk a little bit more about how to operate these and draw conclusions from them, but let's take a look at some basic conclusions we can make. H is going to be a symmetric matrix because if you have well-behaved continuous partials, it doesn't matter what order. Maybe I take the partial with respect to the second variable first, and then the third variable. And then on another piece of paper, I'll take the derivative with respect to the third variable, and then the second variable. I'll get the same thing. And so what that ends up meaning is that you have this nice symmetry between, say, the ith row and the jth column entry as opposed to the jth row and the ith column entry. I hope I said that correctly, but you understand what I'm saying. Basically, if it has a basis of eigenvectors and none of the eigenvalues are 0, that means that we can classify the critical point by using this particular test. If the matrix has a basis of eigenvectors, all with positive eigenvalues, the critical point is a minimum. If it has a basis of eigenvectors, all with negative eigenvalues, the critical point is a maximum. If it has a basis of eigenvectors, some with positive eigenvalues, some with negative eigenvalues, the critical point is a saddle. It is neither a maximum or a minimum. We'll get some practice actually working through this in just a bit on Thursday. Our final topic for the week is going to combine this notion of how to find extrema and the idea of manifolds by talking about constrained critical points. It's a very, very important subject. Comes up a lot in physics and economics and many other areas of mathematics. But here, what we're going to say is, consider a point C on the manifold M, where the function f, which maps from Rn to R, is differentiable. Maybe f has a max or a min at C when its value is compared to the value at nearby points that are also on the manifold, even though there are points not on the manifold where f is larger or smaller. So in this particular case, what we're saying is, I want to maximize or minimize the function f subject to the constraint that the points that I'm considering live on this manifold. They are members of this manifold. So that's why we call it constrained optimization. We're no longer just looking at all of Rn and saying, hey, where's the function f maximized or minimized in all of Rn? Specifically, we only care about particular points. We care about points that live on a particular manifold or a part of a particular manifold. And so that's our constraint. The idea is that we don't consider all the increment vectors, but only the tiny increment vectors that lie in the tangent space to the manifold. The derivative df evaluated at C does not have to be the zero linear transformation, but it does have to give 0 when applied to any increment vector that lies in the tangent space. So that's very interesting. What we're looking at is that the increment vectors in the tangent space to this manifold at the point C, remember that's what this notation means here, tangent space to the manifold M at the point C, they are part of the kernel of df of C. So that's very interesting. When the manifold M is specified as the locus where some function big F equals 0, there is an ingenious way of actually finding constrained critical points by using Lagrange multipliers. But we're going to get to that next week. That's going to be in our final week of material. Not quite yet. So I would say the major issue to take away from this is that what we want to look at when we're talking about constrained optimization is we have a function f. We want to maximize that or minimize that subject to the constraint. The constraint itself is saying the points I want lie on this manifold. They satisfy this particular equation. And so what we're looking at is that we're really only considering the increment vectors that lie in the tangent space to this manifold. And in particular, they need to return 0 when applied to, df needs to return 0 when applied to any increment vector that lies in the tangent space to your constrained critical point C. And so that means that the vectors in the tangent space to the manifold at C are in the kernel of df of C. We'll do a little bit of experimentation with this this week, but really next week is where we're going to kick this idea into high gear and find a really nice, straightforward way to solve these types of problems. That's it for this week. As always, if you have any questions, please ask.